A vector with non-negative entries that add to 1 is called a probability vector. If P is a stochastic matrix and Q is a probability vector, where P times Q equals Q, Q is called a what kind of vector? Steady state. Good. A square matrix whose columns are probability vectors is called a stochastic matrix. Okay. So I'm not going to go through the notes today because we just talked about the most important vocabulary words, and I think that the example will like pull all the concepts together. So you have the notes if you want to read them later, but let's just start with the demo. So City Car One-Day Rental Company has 2 locations, one on Main Street, the other at the airport. Of the cars rented at the airport, 80% of them get returned at the airport. And of the cars rented on Main Street, 30% of those cars get returned to Main Street. Today, half the cars are at the airport. So the stochastic matrix that represents this situation is a matrix where we show where all the cars are from and where they go to. Okay, so I'm going to make a little from. Yes, we have. It wasn't necessarily a stochastic matrix before, meaning that the entries didn't always add up to 1, but it's the same process. Yeah. So I've got from airport from Main Street, and then I'm renting to or returning to the airport, returning to Main Street. Okay, if you rent from the airport, what percentage gets returned to the airport? 80%. Okay, renting from the airport, what percentage gets returned to Main Street? 20%. Right, so if you rent from the airport, 80% gets returned to the airport, which means 20% ends up being returned in Main Street. As long as they're both the same. It could be MA and MA, but they have to be the same. Right. All right, if you rent from Main Street, what percentage gets returned to the airport? 0.7, yeah. And then if you rent from Main Street, what percent gets returned to Main Street? 0.3. Good. So that's our stochastic matrix. The rows and columns are labeled. Today's state vector. Okay, so today, half of the cars are at the airport. Okay, so my state vector is going to be 0.5, 0.5, right? And I'm doing everything as airport, Main Street, airport, Main Street. So this is airport, Main Street. Is that a probability vector? Yes, because the columns, the 0.5 and 0.5 add up to 1. Okay, so what percentage of cars will be at the airport tomorrow? So what we can do is just multiply our stochastic matrix by our state matrix, and that will give us a state matrix for tomorrow. So we just do, yes. So we've got 0.5, 0.5. So when you multiply those, you get 0.75, 0.25. You can have your calculator do it, or you can do it in your head. You do 0.8 times 0.5 plus 0.7 times 0.5. That gives you 0.75. 0.2 times 0.5 plus 0.3 times 0.5 gives you the 0.25. And again, that's airport, Main Street. So how many what percentage of cars are at the airport? 75%. All right, so what percentage of cars will be at the airport the day after tomorrow? No. Yeah, you take the result of that and you multiply your state vector by the stochastic matrix again. So there's our stochastic matrix. We multiply by the state vector from tomorrow, and I'll get the state vector from the day after tomorrow.
This done your population.
We have, yeah. So this is almost exactly the same. The only difference is that everything is in percentages or probabilities rather than just numbers, right? So when we did populations, we had like 100,000, 200,000, right? So now it's all in terms of percentages or probabilities. So this comes out to 0.775, 0.225. So what's the percentage of cars at the airport? 77.5%. Yeah, so it changed really fast in one day, but then it only changed because it went from 50% to 75%. The next day it only changed by another 2.5%. Yeah, so it's looking like we're going to hit a point of convergence. Let's do one more day and see if this conjecture that you are having holds. So 3 days from now, I take my stochastic matrix, 0.8, 0.7, 0.2, 0.3, and I multiply by 0.775 and 0.225. That was the 2 days from now. And I get 0.7775 and 0.2225. Okay, so that's airport Main Street. So that's 77.75%. So I just changed by a teeny little bit there. What do you think it's approaching? 0.7 repeating, we got a 78%. Yeah. So let's do one more and see if either of those conjectures work. I know I said one more a second ago, but we're talking percentage. This isn't number of cars, this is percentage of cars. If there are 10,000 cars, you can have a 0.75%, right? It's just percentage. All right, and then we multiply by our previous state vector, 0.7775, 0.2225, and you get 0.77775, 0.22225. So 77.775% of cars are at the airport. Yeah, so it looks like A is approaching 77.7 repeating percent. There's no, you can't have 0.7 repeating 5 because you can't write an infinite number of 7s and then a 5 because you'd never be finished writing the 7s.
So you're saying
right?
That it never reaches that final number?
Right.
So how does 0.9 repeating equal 1?
No, like.
No, but like for real. Forget about the last 2 years that we've argued about it. How can we not approach 0.5 at the end of this, but we can get 1 with 0.9 repeating?
Because, okay, so it just, writing, say, like 0.1 repeating 3, right, just doesn't make any sense. You can't ever finish writing the ones to put the 3 down, right?
So, but no matter how many 9.
Yeah, but that's different than saying 0.9 repeating 4, right? That's a different thing.
Well, what if it's 0.9 repeating 9?
Then it's just 0.9 repeating. You're just adding another 9. This is not a good time to talk about this.
The problem I have, that approach is 777. The bottom approach is 22.2.
0.7 repeating forever plus 0.2 repeating forever equals 0.9 repeating forever, which is 1. We'll discuss that later. Let's finish what we're talking about. Okay, so the question is, is that conjecture correct, right? Does it actually approach 77.7%? So I want to find the steady state vector. So we think that the steady state vector, some of us believe, that the steady state vector is 0.7 repeating, 0.2 repeating. Okay. Let's actually solve for it and see what we get. So to solve the steady state vector, for the steady state vector, we say we're looking for a vector that when you multiply it by the stochastic matrix, nothing changes, right? So that's what it means to be the steady state vector. That means that eventually things stop changing so that when you multiply this by the stochastic matrix, nothing changes. You just land in the same place. P is the stochastic matrix. Q is the steady state vector we're looking for. All right, so if I want to solve this, I'm going to subtract Q from both sides here. Minus Q. Okay, so I get PQ minus Q equals 0. There's a Q in both terms here. I'm going to factor it out. So this is going to be Q. Actually, I have to factor it out on the right. Because matrix multiplication is not commutative. So the Q is on the right in both of those multiplications. So factor it out to the right. P minus what? What? I'm sorry, I think I'm hearing you wrong. No? What in matrix in matrix multiplication, what is the identity element? It's not 1, I, the identity matrix.
My next test.
I can't wait. All right, so I'm trying to solve for Q, right? Trying to solve for Q. So this is the matrix I want to solve. This is the matrix equation I want to solve. I haven't solved it yet, but H just asked, what equation do I solve? Solve for Q. So I know what P is. I know the stochastic matrix. We figured it out in like part A. And the identity matrix, we know what that is. So then I know everything except for Q, and I can solve for it. So P was 0.8, 0.7, 0.2, 0.3. And then I, 2 by 2 identity is 1, 0, 0, 1. So when I subtract them, P minus I get negative 0.2, 0.7, 0.2, negative 0.7. And then I want to solve for Q, the steady state vector, which has 2 entries, Q1, Q2. Okay, so yeah, I'm looking for the null space of the matrix P minus I. Nice connection. Okay, so I'm looking for Q1, Q2, the entries of the steady state vector that will give me 0, 0. I don't know. That's a good thing to look at in your activities and see if it always comes out that way. That's what teachers do when they don't know the answer. Okay, so how do I solve this? Augment the P minus I with 0, 0, row reduce. All right, so it turns out you get your row reduced matrix is going to be 1, negative 3.5, 0, 0, 0, 0. Okay, so it does. We know that Q1 minus 3.5 Q2 is 0, and that means that Q2 is free. So there are actually infinite solutions here that will solve that system. So give me the simplest one that has integers, right? 2 and 7, yeah. So if you let Q2 be 2, Q1 is 3.5 times 2, which is 7, right? But that's not a probability vector. That's not a state vector because it has to be fractions. So I have to have fractions that add to 1, but also satisfy this.
Divide by 9.
Yeah, so you add them together and get 9 and make those your denominators. So it's actually 7/9 and 2/9. So my steady state vector Q is 7/9, 2/9. So that's sort of a the shortcut to figuring that out. Get the simplest integer solution to your system, and then you have to choose fractions that add to 1 that satisfy the solution, the infinite number of solutions. Only one of those are fractions that add to 1. So 7/9 and 2/9. Does that meet our conjecture? 7/9 is 0.7 repeating. 2/9 is 0.2 repeating. Is 7/9 plus 2/9 1? Yeah. 9/9 is 1, right?
This is why we should do based on.
All right, so that's it for the demo. And go ahead and start the activities. Oops.